This presentation is delivered by the Stanford Center for Professional Development.
Welcome to EE380, Stanford Computer Systems Lab Colloquium, Fall 2012-2013. I'm Andy Freeman. The other course organizer is Dennis Allison. Since this is the first class of the quarter, do a little administrivia. The course requirements are satisfied entirely online at EE380.stanford.edu. Basically, all you have to do is convince us that you watched each of the talks in a quarter. This is not hard, but if you're behind in dead week, we can pretty much guarantee you're not going to catch up. So we have a lot of experience with this. We don't even do incompletes anymore because nobody ever finished. So please keep up. In almost every case, you can view the talks online, so you don't have to come here. That's a huge mistake because 9 times out of 10, something cool happens after the cameras go off. And since there's value to a live audience to the speaker, I'm okay with that. You're here, take advantage of it. Today, 2012-2013, Big Data is an ad on 101 talking about social graphs, customer behavior, the web, traffic in Tokyo, and so on. Today's talk is about Big Data Classic, namely models of physical entities and processes, in this case, the oil industry. This kind of data predates the web, obviously. However, it's still huge, it's still incredibly valuable, and arguably, there are more opportunities for those of you who are typical Stanford students looking for big scores as a startup. Today's speaker, Bob Clapp, is a Stanford researcher involved in changing how the oil industry deals with their big data. Look, 20 seconds.
Let's see. Can everyone hear me? Is the speaker on?
It should be.
Okay.
You shouldn't have played with it.
I didn't touch it.
Okay.
Okay. Well. Yeah. Anyway, I can talk real loud, so I don't really need it. So today I'm going to be talking about, as he said, big data in the oil industry. And I'm sure, I would guess that considering you're computer scientists, has any of you ever taken a single geology class? Oh, we have one.
I had a geology girlfriend.
So I'm going to give you a explanation of how oil is formed that would upset any geology professor at Stanford. But just to give you a basic idea of what we're doing here. So what you need to think about is that we have lots of different types of rocks in the earth. If you've ever been to the Southwest, you can kind of see, you see red rocks and brown rocks, and they have these different properties. And there's only really two types of rocks we care about when we're talking about oil. And one I'm going to call a source rock, which has a whole bunch of organic material. And I'm going to talk about sort of a cap rock or a top seal. The big deal about this one is its porosity and permeability are low, so it's going to stop flow. So what you're going to see over time, we're going to get this organic material, given the right pressure and temperature conditions, is going to turn into oil. And that's my little black dots. And over time, those little black dots are going to flow up. Now it's working for sure. Flow up, and it's going to be blocked by this top seal. So oil finding in kind of the 1860s involved finding a hill, putting an oil well on it, and drilling down. It was that simple. So it was, for about 70 years, that's all we did, was basically find hills where other people had found oil and put down, drill a well. So this is a picture of actually one of the first wells in the United States from the 1860s, and it turned out to be one of the most productive fields ever in Pennsylvania. Okay, so that's how we're going to start. We're going to start with the 1860s, and I'm going to work forward from there. So by the 1930s, things weren't, we were running out of hills, or at least hills we can see. And this is a picture of what's called an anticline. And you can just think of an anticline as a hill underground. So, you know, at some stage you had some pressure that pushed this what used to be a flat layer into this anticlinal structure. And then over time, a bunch of sediments came on top of it, so you can no longer see your hill. So there had to be a way, or what was interesting to the geoscientists of the period was to try to figure out a way to see hills below ground. And that's what started in the 1930s, the seismic reflection method. And so I'm going to go over how we nowadays, almost all oil is found in the world. So you start with a model of the Earth. And this is a really simple model of the Earth. I just have velocity, and I have two of them. A flat Earth, yes. 2 kilometers per second here, 3 kilometers per second. We always put trees, so you know this is the surface of the Earth. And then we make a big boom. We use, this is dynamite. Then it was all dynamite. They would actually set off some dynamite at the surface of the Earth, and they would record what's happening. So we're going to put that. We're going to kind of put this dynamite at a location. Then we're going to measure the ground motion of the Earth at several different locations. And these are what we call geophones. And what I'm going to show you is a computer simulation of Earth, a source generating an acoustic wave at this location, and I'm going to have it go down and see how it goes through the Earth. So let's see. You can see here's kind of a spherical wavefront that's coming down. I'm showing you these blue lines represent kind of rays, so that's sort of a constant angle. When they hit this reflector, some of the energy propagates through, but some of it goes back to the surface. And we record it. So I'm going to show you that movie again, but this time I want you to watch the panel over here. And this panel is what we recorded at the surface. So now all we're getting right now is kind of what we call the direct arrival, which is energy coming directly from the source along the ground surface. But eventually what we're going to see is this, I don't know with the lights on if you can see it real well, but there's an event right here that's coming up, and we're going to see it in our data right at this location. So that's kind of, that's the type of data. And we do this a lot. We're going to do this experiment over and over again, and how many times we do it and how big this data tends to grow, I'm going to get to in the talk. But this is what our data tends to look like when we have done a process called migration, whose job is to take all these recordings we make at the surface of the Earth and somehow make a picture of the Earth. And if you've seen a picture like this, it's going to seem really weird, but you can imagine that at every change in rock type in the subsurface, a reflection is going to happen. Now that reflection is not going to, we're not putting in a we're putting in a band-limited signal, so you can imagine that reflection is going to be convolved with the wavelet we're putting into the Earth. Now, in addition, we unlike kind of when you're doing an MRI, we can't put receivers and sources everywhere. We can't bury a source way down here. So we're not going to do a perfect job being able to recover the picture of the Earth. And we have one other huge problem. To kind of make this picture of the subsurface, we have to know the velocity, and that's something we have to estimate from the data we collect. So we tend to make pictures like this. Really, we have 3D picture of the Earth. I'm just showing you a slice out of it. And these data volumes can be very large. So this is a picture of one of the very first seismograms from the 1930s. And you can see there's, at this stage, about 6 recordings, and you can barely see these white lines coming at. And they were using, in the 1930s, that to kind of get a picture of to find these anticlinal structures under the Earth. Okay, now I'm gonna go forward another 40 years, and I'm gonna tell you how things changed again. Let's say they didn't find all the anticlines, but they found a lot of the anticlines. So the next thing was to actually get better in figuring out where there was actually oil. So I'm going to show you another little geology lesson here. Now, this source rock that has organic material also is going to have some water. And one of the things that happens is when this the fluid flows up, the oil will tend to be above the water. Now that's going to introduce a strong reflection coefficient. So if we get a strong reflection coefficient, we can actually see that on our data. And believe me, this seems very obvious to someone that spent years looking at this. This right in here and right in here are higher amplitude events in the data. And those higher amplitude events can correspond to an oil-water contact, which can correspond to some place to drill. So that was that's what we were doing up to the 1970s, 1980s. Well, the 1980s on has seen a dramatic sort of change in the amount of the volume of data we're collecting and the complexity we're using to try to form pictures of the Earth. And a lot of that has to do with how most of the large oil fields in the United States have been found in the ocean recently. And salt causes us nothing but problems. And let me try to explain why. So salt, this is a picture of a model of what the Gulf of Mexico looks like. And you can see sort of the blue colors are low velocity and the hot colors are high velocity. So right here, you can imagine this is about 1.8 kilometers per second versus 4.5 kilometers per second. Yes?
Is this looking down through the water, or?
Oh, the water is right here. This is a huge, this is 4 kilometers or 2 kilometers of water right here, this dark, dark blue. The sediments have approximately the same velocity as the water to begin with. They increase with depth. Here, you can see that the salt body is almost touching the surface of the water.
This is salt?
No, this is salt. This is actually huge salt bodies in the Earth. They're all over the Gulf of Mexico and other locations throughout the world. And what I'm showing you now is a model of propagating energy through, from this point to the surface. This red line here shows you sort of where we put our recorders. And this is where we start running into problems. If you notice, a whole bunch of this energy didn't go up, it went this way. Now all that energy going that way means that we're not going to record energy from this. We're not going to record very much energy from this location in the subsurface, which means we're not going to be able to do a good job estimating the velocity to make our image, and we're not going to be able to produce a very good image. So this is kind of in the 1990s. A lot of our work was to find salt to find oil at the edge of this salt. That's because when this salt comes up from down here, it tends to make these beds tilt up. The salt acts as a seal, good location for oil. So it's that same idea. The salt is a cap rock. You have sediments that get you have fluids that get trapped by that cap rock. So that was kind of the 1990s. And the 2000s have seen even more of a problem as our targets have shifted from the edge of salt to undersalt. So all the complexity at the edge is made even worse when we're trying to form a picture under these salt bodies. And we have a real problem because most of the energy, and we only get energy from below the salt at very small angles if we have kind of a standard recording geometry. So this is kind of where the oil industry has been moving really in the United States and North America in the last 150 years.
What
Yeah.
are the geographical extents of these salt bodies?
This can be 10 kilometers. Yeah. So it's quite big. Now I've just talked about geology lesson, and I am far from a geologist. I've probably taken more geology courses than you, but it's never been my favorite subject. What I'm going to start talking to you about now is the data we acquired. So what I'm showing you here is a plot, and this is offset X and offset Y. And this is kind of where we set recorders versus where we have our source location. So you can imagine we have a source here, dynamite. We have lots of cool sources. We do dynamite. We have big thumper trucks that we vibrate on the ground. We have air guns in the water. If you're talking smaller scales, I've shot guns into the earth to make waves, and I've hit metal plates to put in sound waves. We do a whole range of stuff in here, but we put a bunch of recorders, and I'm going to show you how kind of those recorders have grown over time. Now here I'm going to start with the 1930s, and we had very few recorders. The 6 was the example I was showing you. They're pretty close to the source, and there's another big approximation we made. We assumed the Earth was 2D, and we only put recorders sort of along a line in 2D. Now as time moved on, we're now to the 1970s. The number of recorders increased. You can see we went all the way up to 48, and the distance between the source and the receivers increased.
Is that plan view?
Plan view. So this is a weird view. This is take the source location, take where you have the receiver, subtract them in a vector sense, all on the surface of the Earth. So in the 1970s, our cables got longer. In the 1990s, by the 1990s, we had decided that the Earth was actually 3D. Or better put it, we accepted the Earth was 3D, and we accepted the only way we were going to make good pictures of the Earth was to accept the 3D nature. So instead of kind of having a single cable, we started having multiple cables. And that meant we started having boats that had cables that were 4 kilometers long, and they may have 3 of them. And we would be pulling these for a 50-mile square region sometimes. Well, not maybe that big, but pretty close. So we ended up seeing this offset range grew a little bit in this Y direction and got longer in this X direction, and that receiver count started going up. As the 90s progressed to about 2000, basically the number of cables pulling behind these boats increased, the length of these cables increased, and the receiver count starts going up even more. The last 10 years has seen a dramatic increase in kind of the number of channels we're using to record data. As we figured out that we can make substantially better pictures in these complex areas if we're willing to go to sort of to expend more money for all intents and purposes. We're starting to have multiple boats in a survey, and we're starting to fill in this panel. So that receiver count you're seeing is 25,000, which is not atypical now. Yeah?
These receivers are on the surface of the Earth?
They're actually 4 meters down. Just the guns happen to be 4 meters, but they're close enough, yeah.
Who's ahead of whom in sonar technology, you or the Navy?
In sonar technology. They're different. They're aiming for different things. They're not equivalent.
Navy contracts the oil industry.
For some things, yes. The oil industry, the technology in the oil industry, some of it is totally cool. They have self-guided robot vehicles that will go and put these recorders at the
UVs, as it were?
No, it's self-guided. So
Underwater.
underwater vehicles that are able to figure out where they are and slowly guide themselves down with virtually no power, and put receivers at the ocean bottom. I mean, we've got some really cool, weird stuff that people spend a lot of money on.
Some of them have the odd diameter of 21 inches, which is about that of a torpedo tube.
Yeah.
Maybe there's a reason.
Yeah. But so anyway, I was saying that's a receiver count of 25,000. Now that 25,000 doesn't sound like much, but we're going to go and record for 14 seconds at 2 milliseconds, and we're going to do that same experiment hundreds of thousands of times for one survey.
Why do you do it so many times?
Well, part of it is we are trying to make a picture of an Earth that's 20, 30 kilometers by 30 kilometers long, and to really get a good picture of it, we've got to do it every 20, 30 meters. in X or in Y or X and Y.
So you're moving the excitation?
Yes, we're moving the boat. That you can imagine we're moving a boat. We're moving several boats. They're going here and then turning around and going through this entire space.
Super resolution.
We're working on that.
The receivers stay fixed?
The receivers in marine are being pulled on large cables behind boats. So they stay fixed
With respect to the excitation?
to some level. We have things called waves that screw us up. Waves will pull the cables.
Lying behind it.
Yeah, we have lots of things that mess us up. We also get shark bites on the cable. We get lots of interesting things going on our cables. But now I'm going to give you the growth in the data size. I'm going to start in 1990, but this is a weird chart. So one of my hats is I work for the imaging group at Stanford. And we get data from the oil industry, but we get a little bit older data, so data that's a few years old. But that's easier for me to figure out, kind of go and look when we got a data and the size of it. And I want to show you the growth over the last 20 years. In 1990, we were getting 2D data sets, and they were in the hundreds of megabytes in size. By about 1995, we had our first data set with these multiple streamers in 3D. And now we saw our data, we're starting to see data volume of tens of gigabytes. We got more cables, and we started getting larger. The data set we got in 2010 was our first multi-azimuth data set, and it's now, it's still a teeny-beady data set as far as the oil industry is concerned. It's about 30 terabytes. So we have really large data. The oil industry is dealing with data sets that are half a petabyte in size for a survey. Now, there's another problem. As I said, we're trying to make a picture of the Earth. So we have some cost. It's not just really large data. Unfortunately, we also have the cost of making that picture of the Earth, which we're doing in more and more complex ways. So here, notice this log linear scale. I'm going to now sort of multiply that by the cost of our algorithms. And I'm going to do it in kind of a naive way. So if we're really stupid on how we implement them and you just do kind of a straight op count or straight memory read sense, this is how the picture goes. So you can see from 1990, we've gone from this cost to, I don't even want to count the orders of magnitude increase. It's a lot. If we kind of normalize that to 1995, you can see that we're dealing with, between 10 and 100,000 increase in the cost of making the picture of the Earth. So, and I wanted to give you a comparison on some things you're probably a little bit more used to, just to show you how expensive in comparison our things have grown. So this is kind of a standard disk size. I went and found a whole bunch of ads for computers going back quite a while. And here's the growth of PC disk size over that time. Now here's PC disk speed. Here's kind of clock speed of a 386, a 486, Pentium Pro, Woodcrest, Nehalem. Now you can notice the turnover point. We multiply by cores. Again, that looks sort of right. And now let's compare them all. So this speed's increased about a couple 120 times since 1990 for a standard simple disk, not SCSI in 1990, just a standard disk. Disk size increased about 20,000. Speed versus core is in the 1,000 range. The stream benchmark, you guys all know what the stream benchmark is? Okay, maybe not. Stream benchmark is how fast you can read contiguous blocks of memory. So it's increased quite well. Our data size is increased at about 10,000 times. And our data size times imaging, well, that's kind of off the charts. And that's our problem. We really have started using more and more cycles over time. And we were using a lot of cycles back in 1990. So another way to look at this, how bad our problem is, come on. And my computer's decided to freeze on me. That's an interesting. Come on. Well, we're going to wait a minute to see. completely freeze. Time has stopped moving according to the computer. Okay. Oh, we got some life. And I have nothing. Ah, I've got something now. Okay. And, oh, and what happened? Okay. So let's start this again. Tick tock. I am dead in the water. I'm going to assume it really hates that slide. Anyway, well, this is coming. So what I was going to say is that basically what we're doing now is far from what we want to be doing. We have seen, we are right now have a target that is about 10,000 times more expensive than what we're doing currently. So we have a big need for coming up with ways to actually make our algorithms faster. And we have life. We have life. I'm getting off that slide real fast. Okay.
The higher the resolution, the faster you find oil?
No, it's not faster. It's the target is getting more and more complex. The only way we can make a good image is actually to acquire more and more data and use a higher and higher approximation of the correct physics. This is a whole bunch of ways we get a picture of the Earth. We know that every one of these, even this one that's 10,000 times more expensive, is not accurate. It's still an approximation.
Okay. That's for the image, but does that mean the higher, the better the image?
It's the only way we
accurate for all, or is there a level of resolution that after that?
We're far from it. We can't, right now we have a resolution of below salt of, let's say, 40 meters. We need a resolution of 5, 10. Why? Because we're drilling wells from the surface, and if we kind of miss, that's $50 million, $100 million down the drain. So some of them, well, 40 meters is pretty big. 10 meters is pretty big. If you miss kind of that slot, you also have the problem you may run into something that kind of causes a well to explode. You really need to have an accurate picture of what the subsurface looks like.
That's why.
Yeah. This is just showing the kind of the growth we've seen in even the last few years. So we're just seeing this rapid growth in the needs. So now I want to kind of give you a few sort of interesting stories here. In the 1940s or 30s, there was a company called GSI. Does anyone, you know the GSI story, huh? GSI was a seismic company that in the 1940s got a bunch of government contracts to do something that actually didn't work for seismic. Then those guys turned into Texas Instruments. So the green building you see on campus, that's one of the founders of Texas Instruments. He's actually a geophysicist. Now here's another one. You guys, who invented the FFT?
Tukey Cooley?
What year was that written?
57?
Or 64, I think.
The astronomy guys.
Yeah. Well, actually, Chevron was using it in the 50s, and it was a trade secret. And the first clustered seismic processing was actually in like 1989, 1990. So we've been doing stuff with technology for quite a while. In this group, specifically at Stanford, I wanted to show you some of the computers we played with. We actually had the second Unix license at Stanford for you helped get for a PDP-11. we moved on to VAXs. Then we moved on to a CM. We had a CM1, Connection Machine 1. We had a CM5. We had a power challenge. we built our cluster. I gave a lot of blood to actually building that cluster. And in the 2000s, it was kind of recognized the growth of computation within Earth science, and they started a new center for helping people with computation, and through some donations from Sun. And kind of in the late 2000s, we started a new consortium that sort of worked on oil industry problems and technology. So this was kind of how talking to with a closer relationship with a bunch of providers of technology on how we could actually improve and speed up our algorithms. And in some cases gave ideas of how those architectures can be changed to better serve us. So the latest and greatest NVIDIA card, remember there's two of them. One of them was co-designed by someone in the oil industry. Because our needs are that great, we buy that many of them. And now, the growth in sort of the need for computation in their science, we've about increased by a factor of 30 our computational power in the last 7 years. And people are still complaining that we don't have enough. And we have a lot of things going on in the School of Earth Science as far as computation. Seismic imaging, which is what I do, reservoir flow, multi-scale, multi-physics simulations, geostatistics, computational geomodeling, global seismology, earthquake source mechanisms, ocean modeling. That's just a subset of all the things that we have going on. And the ones I'm most, because I've been involved in kind of computation for the oil industry for almost 20 years now. So I'm going to really concentrate on those. And I'm going to show you, this is kind of some of the things we do in the oil industry. We seismic images, we have gravity and magnetic, we have reservoir flow, and these, you can think of this as really dealing with wave propagation, diffusion, fluid flow, and here are kind of the core kernels for those algorithms, when we can write those kernels in a different way. We're really doing convolutions, FFTs, and sparse matrix vector multiplies. That's what we're dominated by. Because our stencils are not large enough. They don't win. It's not even a close competition, actually.
You call it a stencil?
Yeah, but so what we're convolving with is a stencil that it's like a jack stencil. Okay, and it's maybe 15 points long, or in each direction. And if you go and if you compare that to an FFT implementation, it's not even close in speed comparison. And believe me, we've done those tests ad nauseum.
Sometimes the FFTs are slow.
Yeah, it's because FFTs are slow. So anyway, so I'm going to talk about 3 different types of platforms here. The first is kind of a CPU, and I'm going to repeat the same example where I'm applying a second-order difference. You guys should all know how this works on a CPU. We're going to kind of load things from some memory level into registers. We're going to scale, add, multiply. And to get performance, we're going to go in, and we're going to try to maximize the pipeline, minimize the number of RAM accesses versus cache accesses. And nowadays, we're going to use vector units. If we're going to parallelize this, we're going to go in and split this array onto different cores and see what type of speed we can get. On a GPU, has a series of different memory levels, from shared memory that's very fast to global memory, which is big but not big enough as far as we're concerned, to kind of the memory on a machine. If we're going to go and apply something like this on a GPU, we're going to put into shared memory to kind of maximize our performance. We're going to break up out to different threads. If you're on a GPU, you're going to kind of trying to have more threads than cores to hide memory latency. All this stuff you probably know, or you will at some stage take a programming class on GPUs and learn. So we play with these. And the third one is a little bit different. And we play with FPGAs. And we actually did, we had someone from a big oil services provider here for a couple years. And he did this big test. We sent out one of our core codes to everybody we could find that did anything with FPGAs and said, how fast can you make this? This company, Maxceller, was the only one that got any decent speed that could beat our good CPU code by any factor. So, and what they do is they have a completely different model of how to do computation, and that's this data flow. So you know, forget your von Neumann programming style. You have to accept a different programming style. And I'm going to just kind of go over their programming style pretty quickly here. So their whole idea is you're going to flow data from some attached memory. So they put a whole bunch of RAM on an FPGA or right next to an FPGA card, and the computation is building these compute units that are going to do a series of steps. You can think a big pipeline, and your data is going to flow from here, do a bunch of work, and flow out. And I'll give you an example of that. The important thing that they have, which really gives, which is one of the reasons this is actually useful for some of our application, is FPGAs have what's called block RAM. And on big FPGAs, they have a lot of it. So we think of this as temporary storage of you know, a couple megabytes that you can access at a terabyte per second. So it can be really useful for some of the things we do. So kind of as an example, I'm going to flow an array that's 1, 2, 3, 4, 5, 6, 7 out of this memory. I'm going to build a series of compute units. One's going to multiply by -2 and a couple of adds. And we're going to kind of flow the data through this. And we're basically building a big pipeline. And what the FPGA enables you to do is if you have a big enough pipeline, even though its clock speed is really slow, if your pipeline's a couple hundred long, this suddenly, even with that low clock frequency, can be a big winner. And there's another thing where it can be really interesting is these compute units can be things like compression and decompression, which can pay off for some of our problems. So we just flow it through, and to get good performance, we maximize pipe length, and we maximize the use of the block RAM when it's appropriate. So I'm going to give you my architectural view in a couple different ways from simply a geosciences perspective. We've got one way to look at things is in terms of pipeline, cores, and hertz. And if you look at this, you know, you've got Intel running at 2 gigahertz, a little bit faster, a little bit slower. It's got 16 cores plus vector units, pipelines of about 15. NVIDIA is a little bit slower, huge amount of cores. Pipeline, it depends how much of the GPU stuff you can actually use. And you've got things like Maxeller, which is running really slow, has, you know, a few cores, depends on your application, and you can have really large pipelines. Another way to view this, which is often more important, is if you're really trying to get performance, a lot of performance is how much of the stuff, how many reads can you do in a fast memory versus how many reads you can do in a slow memory for our applications. So here's a whole bunch of, here's kind of the fast memory sizes and kind of a couple of the different memory levels. On Intel, you can have a really big main memory, but you pay a big latency penalty. And decent size fast memories, small shared memory on a Fermi card, but you know it's quite fast, and you pay a penalty if you have to go to global. And the FPGA, again, as I said, has this really large, fast, close memory, which can be useful. So what we found is, and I'm going to show you sort of examples of this, the more random the access, the better. If you're running on a standard Intel, to win compared to the other two, you really don't want to do random access anyway, but to win. The large memory can be quite useful in a lot of applications. And you know, and when you can't get that much from pipelining and parallelism, this may be your only choice. If you do it for us, GPUs, the more data parallel, the better. The more memory band limited the application, the better. And if hiding memory latency can help, and you can do it, it works pretty well. For Maxeller, large pipelines, if you get an advantage with this large close memory, it can be good. And compression. And compression can be a big friend in a lot of the stuff you do. That's where we sometimes see a big gain. If you can compress the stuff you need to read from memory by a factor of 10, It's hard to compete with an FPGA solution. If. That's a big if on some time. So I'm going to show you a series of examples here. The one I'm going to spend the most time is called reverse time migration. This is like the way, this is the kernel we use for imaging seismic data now. Then I'm going to talk about kind of the advantages and disadvantages of some of the tricks we make to make it economical and how those play on different platforms. Then I'm going to talk about some sparse matrix vector work, interactive pre-processing, interactive deblurring, and I'll end after that. So let's reverse time migration in a minute. So if you remember, I showed you waves propagating through the Earth. Reverse time migration, that's what we're going to basically do. What we're going to do is say, we have some model of the Earth, and we know where we injected energy from dynamite or thumper truck or whatever. Well, we're going to form a cube or a multi-dimensional space. So in this picture, it's a three-dimensional space. In our real problems, it's x, y, and z. So we're going to kind of take this, and we're going to advance it in time, the wave field in time. So we're going to have a sourcing function. We know what source we put into the Earth, or we hope we do. And we're going to advance it in time. And how are we going to do this? We're going to look at the wave equation, which is it's really not showing up well. Anyway, well, we're going to look at the wave equation, which is basically saying second derivative in time, or with respect to time, equals kind of a spatial derivative times the velocity squared. We're going to turn that time operator, that time into a time difference operator, put all the knowns on one side, all the unknowns on the other side, and now we have a way to advance this wave field in time. And we're going to do this kind of forming a 4D volume of x, y, z, and time of this wave field propagating. So once we've got that form, we're going to do something else. We're going to do where the reverse time comes from. We also recorded some data. We know where we recorded it. And we're going to say, well, we recorded this data at 4 seconds at these locations. And we're going to inject that into our Earth model. We're going to notice that this wave equation, we can put the knowns as giving us t plus 1, or we can put the knowns as giving us t minus 1. We can do either. And we're going to run time backwards. So what we're going to do is we have this data. We're going to inject into the model what energy we recorded at, let's say, 3.8 seconds. We're going to propagate everything else in our model. And we're going to fill another cube going from t max to 0. Then our imaging condition is going to be taking these slices that are at the same time and multiplying them point by point. So our imaging condition looks something like this. Sum over all our shots, sum over all times, multiply source and receiver at every vector location x. To give you an idea on op count here. So I'm going to op count and memory reads if you're stupid, if you're doing something really stupid, are about the same order. So I'm going to talk about them as the same thing. So first we have the number of shots. Then we're going to have our volume size. We're going to have the number of time steps we need to advance. We have to deal with stability concerns, which are going to mean we're going to have to advance at a finer sampling than we really want. And we're going to have the stencil we're going to use to advance the wave field. And that's going to have a certain number of elements. So that's going to be our cost. Now if I can put numbers to it, those are some typical numbers. So 5, 12, 15, 10 to the 17th. So that's not a small number. We do not run this on our iPod. So we spend some effort trying to get the cost of this down for some strange reason. We actually want to have an image at some stage. And we do this in a lot of different ways. One is, as I said, everything is maximizing things in close memories. Now how you do that? You do domain decomposition. So, but our problem is kind of different. So you would think this is normally how you do domain decomposition. Make big rectangular blocks and go on. Well, we've definitely tried that. You could also think of doing pencils. And if you're, And if you think about those, we have these overlaps. If you notice, these things overlap, and that's because you do domain decomposition. We have that filter. It has some width. And that width is going to, that kind of, any of the samples that go on that boundary have to be sent to more than one block. If we look at sort of kind of trying to fit things in L2 in a standard problem size, we may have 50% rereads. So that means how many elements have to be read by reread by more than one block using pencils, and 35% for boxes. But we do pencils, and I'll show you why. Because you don't need to think of your problem as static. So what we're going to do is, this is how much we can afford to put in L2 cache to compute the wave field at this location. Well, as soon as we're done computing the wave field at location, we can dump, or on this row, we can dump this entire row, read in the next row. And we can continue this process all the way down. So we're actually doing pencils all the way down, and that's going to give us the best reuse. So this is just basically flush cells that you no longer need. And to give you an idea on the performance, I stole this from one of the students. This is his work on writing a code like this over time. And he started with a serial version and increasing nodes, that should be cores, as he went on. And really, where you really see something interesting is the GPU. He learned how to use shared memory, how to do pencils, and here was his performance gain. So this is why using pencils is kind of important to us. So now this is kind of linked with something else, which is our filters. And we have a problem beyond kind of just stability. We also need to be concerned with dispersion. And you can probably see, as you follow around this oval, that the wavelet changes. It shouldn't. This is from numerical dispersion. And we don't like that. That messes everything up. And there's a couple ways you can solve this problem. You can do smaller time steps, smaller grid cells, and live with it. Or you can do a higher order approximation of your difference operators. So instead of a 3-point stencil, you can make them bigger. And here's kind of why you should go and do that. You use a higher order stencil, the volume size for the same level of dispersion decreases. And it's substantial. We can decrease it by a factor of 8. But there's always a penalty to everything you do. And you have to consider the amount of reads you're going to have to do. Because the reads are going to increase as the stencil size increases. But that's, again, the naive way to think about it. What really matters is reads from an expensive memory. So I just added a line here. Can anyone see it? It's right here. This is the reads from expensive memory. Because we're putting something in a cheap memory, it's not costing us much. But this is a certain cheap memory. This is the FPGA block RAM. So this is saying, because we have a really large cheap memory, we can kind of reduce we can kind of get away with these really large stencils. If we look at a GPU, you can see at some stage right around here, it suddenly becomes a bad idea. That's a much smaller close memory. And a CPU is somewhere in between. Basically, it has a turnover point right in here. So that's a game where an FPGA is the best, if that trick is useful for you. Another one, kind of at the other end, is variable sampling. We have the stability and dispersion constraint. The stability one is a function of our time sampling and the velocity and our spatial sampling. What we can think about doing is changing our sampling. When we have lower velocities, we can use smaller cells. We get higher velocities. We can use larger cells. Now, this is, again, a question of data parallelism. As we move from a CPU to a GPU to an FPGA, the size of those blocks that become something useful must increase. So on a CPU, you can make these blocks quite small and not really pay a penalty. On a GPU, you still need 10,000 different parallel tasks to get decent performance. On an FPGA, you don't really want to change much of anything. So it's kind of the other argument. The CPU can work with this better. Now, another way to use a large cache is what we call cascading. Remember that CFL factor. We have a whole bunch of imaging steps, or steps where we have to propagate the wave field. We don't care. And we can play tricks by saying, well, at some stage, as we go through this volume and we've advanced the wave field, when we reach this location right here, we now have everything we need to start advancing the wave field here. And we can kind of do this cascading. And this allows us to do lots of different time steps. At once, we pay a penalty of needing a larger kind of close memory in size, and we're going to do more compute. But if you're really if you're bound from the cost of reading from main memory, it's a nice trick. And the way FPGAs are growing, it's the only one that's really increasing the size of their close memory. It's something that's useful there. Now, there's another big difference between what we do when we do a physical experiment and what we do as a computational experiment. The computational experiment has boundaries. We got to deal with those. We don't like those. So we have to introduce a boundary condition. And we can introduce an absorbing boundary condition that's pretty simple, that sort of damps wave fields, something that tries to kill slopes that are at a certain angle to the boundary, or something really complex. This is the best going down in quality. This is the least parallel going up in quality. Guess what? If you're doing a CPU, you're going to do PML. GPU, FPGA. This is kind of a story that repeats itself. So here's the RTM cost with these tricks and a couple more that I mentioned. We're basically 100 times faster. We now have something we can actually use. Now, there's another problem that I didn't mention. And I don't know if anyone caught it. I said we're going to advance this wave field, and then we're going to advance this other one in the other direction. And we're going to correlate them. That means we've got to store this wave field. Now, how big is that wave field? 1 billion points that you're going to do 1,000 time steps. And so you're storing this to disk. Your speed of disk is slow. You've got a problem. So we go in, and I just want to, so that kind of shows you this speed versus speed is core, and it's getting worse. So we've come up with ways to go about to solve that problem. One of the things that we've come up with is we store checkpoints and redo computation. But we also have played some games. And I'm going to show you one of the games we've played. So this is that imaging condition. What if I introduce noise to that imaging condition? Well, I'm stacking over time, 1,000. I'm stacking over shot, 100,000. If I introduce random noise, it's gone. So can I play a game to actually introduce some random noise that'll do me some good? And that's what I'm going to show you here. So what I'm going to do is I'm going to say, well, what would be really nice is if I could propagate this all the way to the maximum time, and then propagate these two fields simultaneously. Now I only need to store a few copies of these wave fields. That'd be pretty good. So when can I reverse my propagation? Well, as soon as I introduced all those boundary conditions I just showed you, I can't do it anymore, because those are going to kill all the waves that go to the edge. I can think about being a little tricky. And this is how I'm going to be tricky. I'm going to introduce this bizarre boundary here. And this boundary is going to get more and more random as I get to the edges. So what is it going to do to the wave fields? How's that look for a messed up picture? So this is a wave field advancing in time, and it hits this boundary and suddenly becomes randomized. Now here's the cool thing. This is the wave field at 3.6 seconds. I can take that wave field and reproduce this picture to machine precision by going backwards. And all of those errors from my imaging condition, here's using kind of a standard way. Here's using that random boundary. They stack out. So we can play games. So the question is who wins? And the answer is everybody, nobody. All three of these type of architectures are being used in the oil industry for this type of problem. And all three have their people that are sure they're the best in the world. And it all depends on what they're doing. Details. So now let me go through some quick other examples. So sparse matrix vector multiply. This is the one that I don't think I have any applied mathematicians, makes them cringe. So I'm going to do this one first. So this is showing the sort of the range of sparse matrix or sparse vector or matrix descriptions from something that's very structured to unstructured. And as we go along this way, our costs go up per element because we're going to have to use more bytes to describe each element in that array. We're going to have more indirection. A lot of bad stuff is going to happen to us. So one of the problems, we have a lot of problems in the oil industry that involve sparse matrix vector multiply, and these are kind of a couple of them. This is a fluid flow problem, and this is a geomechanics problem. So this is trying to, show how the Earth changed over time. And this is these are two codes from Schlumberger. I stole this slide, and they show its performance as a function of cores. And the thing to notice here is it doesn't scale well. And it's really obvious to think of why. If you're doing a sparse matrix vector multiply, you're doing a lot of reads for very little math. You're quickly running out of memory bandwidth. So they sent this problem to this company, Maxeller, and this was kind of an interesting result. What they did is they said, OK, I'm looking at this matrix. It does have a lot of structure. It's not perfectly diagonal, but it's pretty diagonal. Why am I going to begin with, why am I storing how off it's from diagonal as a 64-bit integer? I can store it as a 4-bit integer. It doesn't really, whatever works. So that was the first little trick. And then they did another trick, and they said, well, I'm solving an inversion problem. At early iterations, why do I need to use a high precision numbers? Why don't I start with low precision numbers and go and increase my precision over time? And that's what they did. And this is the speed up they got. Basically, they were seeing in the orders of 20 to 50 times faster than a conventional CPU node. That's completely constrained by memory bandwidth. And the funny part about this, even with all these tricks they're doing in compression, it still was memory bandwidth bound. Well, they're doing a conjugate directions type inversion problem. Yeah. So and kind of they like this picture, which is basically saying take a rack, do a node. I don't really care, but it was just an interesting way of thinking about where FPGAs can help. Now, another thing that I haven't really discussed too much is other things we do in the oil industry. I just told you all these things are really op intensive. We have a whole bunch of stuff that's not so op intensive, and we tend to do this in a really stupid manner. And it's for historical reasons. Basically, we have a process. We run a huge data set through it. We look at 3% of the data, see if it's good, and when we screwed up, we rerun it again. That's tends, or we do something even worse. We window it out to a test, find out it worked there, and then it screws up somewhere else. This is our model, and this is from a historical reason because a lot of our processing systems were written in the 90s when it first became, written and have been expanded greatly, but written in the 90s when it first became reasonable to store data on disk rather than tape. So things have changed since then. Here's that same picture again, and specifically look at disk speed, memory speed, and data size. And I'm going to have a look at it a different way too. And that's showing that basically if we take the RAM versus disk speed, we've seen RAM speed increase order of magnitude more than disk access speed. And so compare that. So it was a factor of like 12 then. It's a factor of 100 now or more. And we've seen data size increase at it's increased by significantly less than an order of magnitude. And what does that mean? One of the things you can think about doing is using main memory as a large buffer. We can never hold our problem in memory. It's just not going to happen. They're not going to. By the time they invent a computer that can hold 100 terabytes, we're going to be doing 100 petabytes. That's just reality for us. But we can kind of start to do stuff that's interactive. And that involves kind of building a dependency chart to figure out, if we want to display this pixel and we're doing these operations, what do we need to read from disk? we can kind of do games like this, and I'm going to show you an example of that. But we need to think about hardware considerations. We're going to have semi-random access. It's going to be read-dominated because we're going to have the read from disk, do a bunch of operations. We're displaying it on the image. So as far as I/O from disk, it's all read. It's going to have limited parallelism. So guess what platform we decided to deal with this on? Any guesses? CPU. Yeah. But we went and did a little twist. We got something called EcoRAM that is dead, but it is cool for this application. Anyone know what EcoRAM is? EcoRAM was solid-state memory plugged into a processor slot. And this is why it was cool for this example. This is kind of semi-random access of a large volume. So we have a 0.5 terabyte of this sitting around. And here's kind of disk speed versus RAM versus the solid state. And it's a heck of a lot closer to RAM than it is to disk. So we're putting a 0.5 terabyte of data, which for the application I'm going to show you is more than sufficient on this very fast memory. And we can now play games with it. So this is showing you locations of sources on a 3D survey. So it reads it from disk. And then we can go, it displays, it displays about 1 million of the 10 or 100 million different locations in here. And we can interactively play with it. And if we decide we did something wrong, we can go and tell it to redo it. It rereads it from this very fast memory and can go back. So this is kind of one of the new games we've been playing with recently. Flash memory. It's flash memory plugged into cores. It's really kind of cool stuff for us. We got it about 3 years ago, but we still use it for applications like this. Now, another one is what I'm going to describe as deblurring. Really, it's an imaging method, but what we're trying to, you can think of it as deblurring. We've got an image, and we can know that we have a deblurring filter that kind of looks like this. So if I take the row of this matrix, this is the matrix I want to invert. We have filters that look like this. We can go in, and if I zoom into one of these, it looks something like this. And we're going to try to solve an inversion problem, which is basically a bunch of multiplications of points are filled with functions that look like that.
Is that a meter filter?
No, it's actually you can think of it as a blurring operator of migration. That's what it is. So if we can invert this, our images will be higher resolution. That's the goal of it. One of the things you can notice, as I'm showing you a movie of these deblurring filters, is they're very smooth. So this is the deblurring filters over X, Y, and Z. And they're smooth functions. So if they're smooth, you can subsample them, compress them, do lots of different things. And we can compress them quite a bit. We can compress them to the point that we can hold portions of them in things like shared memory. And because we're decompressing on the fly, we can have a reuse factor of rereads of shared memory of 30x. We can do linear interpolation to go beyond that. And this is an application that works really well on GPUs rather than FPGAs because the bandwidth for our GPU is 3 to 5 times that for an FPGA. It's better than a CPU because the compute level we're doing here, this is like, if you want to have something that makes the GPU look good, this is a problem that makes the GPU look good. It's incredibly data parallel, and it involves a ton of reads from shared memory, which you control so the computer can't screw you up by sending them out of L1 or L2 cache. It works well for us. And we can get from kind of the initial CPU code to getting the best CPU code. The GPU is another factor of 5 or so. Anyone that tells you GPUs are a factor of 100, yeah, there's something wrong. But so overall, that's about a 30 speed up. So I'm running out of time, so I want to end with a few things. So what I've talked about is sort of how geoscience and high performance computing have been together for a long time. It used to be said, and I could not find a reference to this, but I used to hear this all the time, that a quarter of all cycles in the world from before 1990 were for the oil industry. And the second biggest users of cycles before the internet resolution was the oil industry. Could not find the quote for that, but that's what people say. We play around with a lot of toys. I get to play around with a lot of toys. I have a Knight's Ferry coming in this next week. We get toys all the time, so it's really fun. My job is really fun because I get to go and any new hardware I think would be fun to play with, I can get someone to send it to me and get access to it. And the oil industry, they send it because they know the oil industry is a big pot of money, and if they're willing to experiment. Now, I also that anyone that, in my opinion, anyone that tells you that CPU, GPU, or FPGA is the answer to everything hasn't done enough different types of problems. There isn't right now. There isn't a clear winner, and you really need to think about how you can fit your algorithm to different architectures, not just be stuck in this mindset of here's my algorithm. I'm going to always do it this way. There's really the fun is figuring out how you can completely change it to fit something new.
You do some of each, basically.
Yeah. So kind of, and this is what, to really kind of do this, you have to understand geoscience. You have to have some knowledge of computer science. You have to be able to do some applied mathematics. And if you can do that, you're what's called a computational geoscientist. And this is something, a kind of a growing field here. And saying this is a computer science audience. So what they say, what I've heard many oil company people say, is if you come in with these skill sets, we can teach you this. We have a heck of a time teaching people that's got this skill set to get anywhere here. So some conclusions.
Job security.
Yeah, the oil industry deals with large data and large compute. And when we say large, we do mean large. We're not Google petabytes, but we're not far behind that. At the current stage, we don't see a winner. And really, to get somewhere and to get a lot of our problems to be practical involves knowing, at least being able to dabble in a lot of different fields, which is kind of a fun thing. You don't. My day is not looking at data all day. It's not doing computer, writing code. It's all day. I get to do all these different things all the time, and I always have to end with acknowledgments. I have a lot of hats here. I'm with SEP, the imaging group. I'm with kind of this. I'm the manager of this consortium. I'm also kind of the technical director of the computational center at Stanford. So all those give me money. Schlumberger. I stole some slides specifically from Olav Lindjorn, and I showed you one data which was from a company called Total Fina Elf, or Total, I think they've changed their name to, in this presentation. So I am 2 minutes early. Any questions? Yeah?
I may have missed it, but why wouldn't you just look for the pattern that I take it, you create the image, and then somebody looks at it and decides there is all here. Mm-hmm. But there is a characteristic that you can let the algorithm just look for it.
Oh boy, we've tried this. And it sometimes can help you search through a very large volume, but this is not my expertise. A geologist has to, this area has to. It fits this geologist's conception of this is the only way oil could have been formed here. And they're right. I mean, these are $50 million tests. But we do pattern recognition. We do play those games. We do try to search our volumes. We play lots of different games to try to do it.
I'm constrained that the image has to be processed.
So I didn't talk about the velocity estimation. So the velocity estimation involves doing that migration well, it used to involve doing it a few times. The way we estimate velocity now involves doing that migration 10 to 100 times. And we have we have to actually, they have limited leases on these locations, so they have limited time to do these incredibly expensive imaging processes. Then to decide if there's worth drilling oil before their lease runs out. Yeah.
I have two questions.
Uh-huh.
So the first one is, you guys do mostly physical models, but are there like statistical or sort of techniques to do it faster than pure physical?
We play with what we call geostatistics, and we play with geostatistical approaches, and they are useful for some of the things we do, but sort of for wave propagation, they just don't apply at all.
Do you see any applications of like open source, like sort of cloud computing type distributed infrastructure, like Spark or?
I just had a meeting today with some reservoir flow people that were asking if I thought they could use Hadoop to do some of the work. That was a couple hours ago. So yes, is the answer to that. We do experiment with cloud computing. Problems. The problems we have, they take on the fastest GPUs a day to run sometimes. So that doesn't fit the sort of elastic. We definitely can have elastic demand, but some of these companies are running at 90% of peak capacity continuously, in which case cloud computing makes absolutely no sense. As far as sort of the earth science in general, we're part of, I don't know if you guys know, they're eventually going to be moving everybody's clusters to Slack. That's going to happen in the next few years. And the long-term goal of that is to start to have an elastic cloud at Stanford. And so that's going to be some experimentations at kind of the university level of that concept. And I definitely see the need, but we've priced out what it would cost to do Amazon, given we keep track of our usage, and Amazon isn't within a factor of 5 right now for us. That's, yeah. Yes?
It's interesting, the Hadoop question. I work with Hadoop pretty extensively, but it's great for data management. The reason I came actually is we've been trying to do machine learning algorithms in Hadoop, and we're also looking at GPU to doing some of this stuff. I'm wondering if you've done any, you've done mostly computational stuff. We're talking about decision trees and other kinds of.
The newest GPU has some chances.
Yeah.
Yeah, the newest GPU definitely is something I would say that may be, where you have the ability to start threads from threads, is something I'd look at. I don't know. Do you know people at NVIDIA?
Yeah, we have contact.
Okay, well, if you could, there's a guy called Paulius. Have you met Paulius?
No.
I'm sure he's probably listening right now. He's in the oil group, but he's probably, I've met the group, the DevTech group. The DevTech. Yeah. Those are the DevTech people, the ones you want to talk to. Paulius is kind of the best reference for being able to give you an honest answer. So make sure no one else is around from NVIDIA when you ask him. But.
And the curiosity question.
Are we off camera?
I've done some work with remote sensing in my previous life, and I'm wondering if you've done anything like using multi and hyperspectral data to identify potentially interesting areas to drill.
There is some work with that type of data to find locations, but really we normally know from the geology approximately where we want to drill. So it's really finding what it looks like. The targets now are several miles down.
Yeah.
So what you see at the surface.
You can't.
Yeah.
Yeah.
Any other questions? Yes.
So, oil industry has a lot of money. So, do they try to design their own chips? I mean, it looks like
design their own chips.
Yeah, for this kind of computations, because
they for acquisition, you would be the amount of work they do in designing their own everything is huge. For computation, they were one of them was a part, or I don't know what exactly the relationship, but they were partnered with NVIDIA to some level for designing, the other GPU that just came out. There's sort of one they're saying they actually say for oil and gas. So yes, that would be the truth. And actually, some of the work that Max Seller did actually affected, or was one of the things that affected a change in the Xilinx chips. So the answer is yeah, we do talk. you know, as far as Intel, Intel's so big. Yeah. Yeah.
So the oil industry has this big legacy data problem, and what are they doing to get all the stuff off of all the old 9-track tape?
Well, have you? Okay, I was at. Their data libraries are really something to see. So they spend quite a bit of money of kind of just changing the, you know, updating their tape system. And I was at the National Lab up in Livermore.
Right.
And it's a very similar situation.
Yeah, I've seen their classified tape library.
Yeah. So you know, but it's a similar, you know, bunch of pods that can talk to each other. They're doing the same thing. They've got tape stored in, you know, perfect conditions in places. But what we're finding is a lot of the data we're acquiring is changing so dramatically. I don't think the data we acquired from the 70s is all that useful for us anymore.